Hi, I want to talk today about what spectroscopists, especially if they use machine learning, what they could learn from archaeology. And this question might seem a bit strange to ask, but I think it will give a useful analogy for how a very important technique in machine learning operates and to basically give you a metaphor to think about it. So if you think about archaeology, you can think about it in a very high level way as going sometimes through a three-step process where an archaeologist finds some object, some specimen, and then has to remove some dirt from it, will then describe it in a compressed form, perhaps in a notebook, from where then a colleague can take this information and based on this reconstruct the original object. And the process of distinguishing the dirt, the signal from the noise can be quite tricky. It has to be learned by expertise. The compression is quite information rich and doesn't of course contain the dirt, only the most important signal in there. And from there you can faithfully reconstruct the vase, and you did a good job if your original vase is very close to what you then reconstructed in the museum. And the similarities that, of course, if you now look at spectra, they also have sometimes noise in them, and the noise can be very hard also there to distinguish from a signal if you're not an expert. So here we have some sample spectrum, we have a lot of noise in here, and here it might be easy, but it can be way more tricky in other spectra. But you also have a certain interesting phenomenon here that you have a lot of redundancy in the spectrum. So quite often you will observe that neighboring wave numbers have almost the same value also for the peaks. And you see also correlation matrices that you have those big clusters here, and many things are quite correlated, meaning that you can compress information a lot, because if you have a lot of correlation, then storing just one of the values can be then replaced for all the others. So we can see we can perhaps learn from archaeology how to effectively remove noise by being an expert in this, and also how to compress effectively by again being expert in how to distinguish signal from noise and going into a compressed compact representation for our spectra, from which you can then still reconstruct something that looks like the original one. And this is what we will do with so-called autoencoders. Autoencoders go through this two-step process. They encode, have this latent space, and from there decode. And you can think about what they do quite easily if you look at linear autoencoders. The simplest example is shown here. We have points living in 3D here, x1, x2, x3. So each point here would be described by 3 coordinates. But of course, in this example here, one of the coordinates is quite redundant because we have no variation in x3. Thus, we might want to reduce dimensionality here from 3 to 2 because the third dimension is useless. And why should we keep it? So this is our goal, to go to 2 dimensions. And if you kind of listened to your teacher and then the algebra, you can perhaps imagine you can now project data with a projection matrix, which we in this case will call W. So you can now just multiply your data X with W, and in this way go from the 3D space to a 2D space, if K is smaller than D in this case. So if we do for this example here, we just have our initial input matrix X multiply with W. You can just now go through one entry here. So again, we do row times column. So we take x1 here because there's 1 here, and we then drop x2 because there's 0 here, and we also then drop x3 because you have 0 here. So we then have x1, x1, 1 kept here. If we then go through then the second column, we drop x1 because they have 0 here, we then keep x1, 2 because they have 1 in here, and we then drop x3 because here's a 0. And we then have the same pattern over again. Effectively, we dropped one of the dimensions in here. And then we have the data now living in 2D. We can, of course, then do the same thing the other way around, just kind of, in this case, almost transpose the matrix, and then have the data again living in 3D. This example was, of course, quite simple. We can just imagine how a matrix has looked like. We can just kind of write down how this W has looked like, but if your data is kind of living in a more complex world, then separating out this redundant dimension can be, as you might imagine, more complex. So finding ways to determine those W's might be effective for kind of having a good reduction of dimensionality. And this is what we do with autoencoders. And autoencoders, we will train how those W's for encoding and decoding will look like. So basically we will learn effective W's for encoding and then also for going the other way around for decoding. And that's what you can do with neural nets. Because neural nets, in the end, they do nothing else than just multiplying some X with some W and adding some bias. So multiplying with a matrix means you would rotate your space, and then B means you have an offset, you move your space up and down. And that's what you do in PyTorch with linear layers. So we have here two linear layers, one for the encoder, one for the decoder. So we basically go from input dimension number of wave numbers in our spectrum to a latent space. It was before with input dimension 3, we went to 2. It might be something else for re-example. And then we can from there decode for decoder. We go from those latent dimensions to then our spectral dimensions back. And if we now train this model, we do a forward pass in PyTorch, where we go first through the encoder, we multiply with W1 at the bias term, and then we have our late representation Z, and we then decode this to our X reconstruction, or in this case here X hat, by then multiplying it with W2 and adding there a bias term. And we optimize now W1, W2 and the bias terms by minimizing how this different X and X hat are. So we basically try to make sure that if we now pass a spectrum through encoder and decoder, that what we get out after encoding and decoding again is as close as possible to the original spectrum. So you're trying to minimize the distance between the original spectrum and then what you get after pass through the autoencoder. So we basically have to go through bottleneck, and we try to make this pass through bottleneck lose as little of the important information as possible of the spectrum. This is shown here in a different way. We take our spectrum, pass through the encoder, so we now here get the Z through the encoder, and then pass through decoder, get X reconstructed, and we then minimize the distance between this spectrum here and then this output spectrum, and this way optimize our linear layers in this case here. And if you try it out, this works decently well. But it doesn't work perfectly well, and as you perhaps recall from your lectures on neural networks, you can make things more expressive by making them non-linear, because in the end this is almost a PCA. If you would dig deeper, you just do linear algebra here, and you can make stuff more expressive by just now adding some non-linearities, because multiplication just rotates space, addition just moves space up and down, and with non-linearities we can now also squeeze space in different parts of the space. So we now will just keep almost everything the same here. We will just now add to the encoder and decoder a nonlinear function. So we have here in this case a value, a nonlinear function. We just basically have 0 and then this linear slope. And both cases in this case have a way more expressive autoencoder. And you can now imagine that you have a very powerful tool, because you can now compress your spectra and then from this compressed version go back. So even for those things you might want to use an autoencoder, you have a fingerprint and a compressed version of your spectra. So you might wonder, how does this fingerprint look like? And then you can now try to pass a few spectra through the autoencoder, and you will then find those spectra lying in different points in this latent space. So here we just have the coordinates of Z, which is our latent representation. And what you will then find out is that if you just optimize your model in this autoencoder with just this reconstruction loss, minimizing the difference between X and then X hat or X reconstructed, you have no incentive to have the space structured in any particular way. So you have no guarantee that those clusters center around something like 0. So here it's drawn to be around 0, but we have no guarantee that actually will be the case in our latent space. we also have no guarantee that our spectra, if we don't have any points in training in between those clusters here, that this distance here, that those holes will make any sense. We have no guarantee that tells us that the distance here between those clusters make any sense, because the training goal isn't to give the space here any kind of meaningful clustering or distance functionality. We just try to make a faithful reconstruction of our training points possible in training. But you can now imagine that if you now have a decoder, you could in principle want to go from your latent space to new spectra. You could make up artificial spectra. You could now in principle just sample from this latent space and make new spectra. So you could try, if you have now a phase autoencoder, you can have an input phase, output phase. You could now imagine you would like to make fake faces, fake images, deep fakes, by sampling in a latent space and then reconstructing with the decoder. But the problem is, sampling is quite hard if you don't know how and where to sample, because if there are some holes in this latent space, sampling there doesn't make sense. Also, if your distribution isn't centered around zero, you also don't know where to start sampling. So it means that the lack of structure in the space makes sampling for making up new spectrum, making new faces quite difficult. You see it also if you would walk through latent space, you would have at some point quite drastic shifts in how spectra look like, so you have no continuous structuring in the space, which again makes things like sampling from the space difficult. We would like to have something that looks more like this, where we can now have meaningful measures of distances in the space. We can take now smooth continuous walks which transform one type of spectrum to another type. So we have now a way less dramatic abrupt change in properties, which again will make it very easy to make changes in sampling spectra, sampling phases, if we would like to make up new spectra, to train new models, or to just for some reason make them. You can make this also for molecules and make up new molecules, and there it's important you can sample in effective ways from this latent space. So this is kind of to tell you that having some structure in this latent space can be very important for applications. So the question is now, how do we impose the structure here? And this is a bit of an outlook. It will require some more advanced techniques that won't be covered here, and only kind of on a high level. But the goal will be to basically model not only points, but distributions. So we won't now predict z, latent point, latent space. We will predict distribution, the parameters of distribution in latent space, a mean and variance. So you have distributions of latent factors. We can, based on those, get a distribution of spectra. So we have here now, if we sample from here, we'll have a distribution of our spectra x conditioned on our latent vector, and from there we can now sample a spectrum x. So we can sample from our distribution of latent factors, and then based on this have a distribution of spectra, and from this we can sample a spectrum. So we now model distribution. We can now in principle also impose in our training that this distribution should be well behaved, should be for instance a null distribution, a multivariate one around 0. So this looks in practice like this. We'd like to maximize, in this case, our log likelihood of a data. It means that basically the data should be likely under our model distribution. And you basically will see different terms here. We will impose this prior, which you would like our space to follow in the structure of the space. We have then how likely a spectra is given latent factor. And in practice, solving this is possible because this might be here a neural network. And this will be here our decoder, and then sampling through all possible z's is intractable, so solving this integral directly is impossible. The trick will be here that we kind of approximate some parts of this with tricks like Jensen's inequality, and you'll turn out to, in the end, and this is then kind of an outlook for more advanced variational Bayesian inference lectures. But you will have a loss with two parts. That's an important part you should take away. You have two parts here. One part kind of measuring how close inputs and outputs are. As we had before, we just measure how good we reconstruct. But you now also have a new term here, which is the KL divergence, measuring how close your distribution is to what you impose as a structuring distribution. So we measure here how close is our encode distribution to what we have as a prior, as our normal. And this now will impose some structure to our space. In practice, you will do this by predicting the mean and the variance of the distribution. And this will then need to have another trick in training. You will need to basically, because this here now predicts just the distribution parameters and not an actual Z. And to get Z, you would need to sample from there, but sampling makes it possible to backpropagate your gradients, and thus you basically have to move the randomness out of this, which you do with this trick here, where you move now the randomness into a separate part, where you then basically add here epsilon, which is your random factor, times the variance, standard deviation to mu, to have then your latent factor. But this is because you don't predict directly Z, but you predict now factors mu and the variance in here. But this will in the end give you some good reconstructions, but also now a way more structured latent space, where you can go through latent space and reconstruct a spectra way more effectively. And this has been used also for molecules. You can here, for instance, have encoders for molecules, get into latent space and from there decode. This has been very pioneering work in chemistry. A lot of citations, follow-ups based on this. You can do then very interesting things, because you can also now impose some additional structuring factor to latent space by training now also based on that model to predict properties. This will now basically structure the space to then cluster compounds by how the properties are in the space. And you could then even make the directly gradient descent in the state space if the second model is also differentiable. But this in the end is like a very, very quick run through what autoencoders can do. The key ways that spectra can be redundant and noisy. You can remove some of this redundancy and noise by learning how you compress and decompress well with autoencoders. The spaces with autoencoders themselves aren't well behaved and structured. You can fix this with autoencoders, and those can then be used, this variational autoencoders, those can be used also for other applications like making up new compounds. So you see basically removing noise and dirt, compressing, describing things in a compressed way, and then reconstructing from there can be effective, not only in archeology, but also in spectroscopy.